Boom! Here we are. Appendix 11, the last of the math appendices for your Regents Physics course. Slope. MC Hammer hanging out over there talking to us about slope. You'll get your slope right. Slope is one of those things that kind of fools people. They figure, oh, slope's easy. I know how to do slope. I learned slope in middle school. You did. I learned slope in middle school. That's no problem, but here there is a problem because you got to be sharp with slope. Slope is used with experimental data points. You actually have to do an experiment, collect data. Here you go, got a little data table right here. You plot those points. That was the content of the previous video, Appendix 10. You draw yourself a line of best fit. That also was in the previous video. But now you got to make some sense of it. Like, why did we draw this line? Is it just to make it look pretty? I mean, it does, don't get me wrong. But to quote a word that's hopping out at me in the middle of the page, no! We did not just make a line so that it looked pretty. You got to do something with this line. In fact, one of the most common activities, once you have plotted data points and you see that there is a line, is to then determine its slope. Because as you will learn in class, the slope has a meaning. It's not just a number. It's a magnitude. It's got a meaning. All right, so let's go over slope. If you don't do it right, it doesn't work right. You get the wrong magnitude for whatever that meaning was. So you see here, there's some bad and good decisions listed. One of the bad decisions is just using the data table. Not the data table is automatically bad, but just like if you ignore, here it is, put this screen up. If you ignore your plot, your graph, and you just look at the data table and start doing slope, odds are it's going to be wrong. Bad idea, and you're not going to get credit. You have to instead use the best fit line. The best fit line is there so that you can determine a slope. That's why you drew it in the first place. Another bad decision is using just one point. Sometimes what people will do is they look over at their data and they say, oh, look, I see the coordinates of this point right here. It's 2, 5. So 5 is the rise, 2 is the run, 5 divided 2. That's not how you do slope. Slope is not based on one point. There is something called instantaneous slope. We get to that in AP, or maybe some of you are interested. But the standard way to do slope here is using 2 points with a wide stance. What do I mean by a wide stance? Don't use a point here and a point here. They're too close together. Spread them apart. Like use here and here. Yeah, that's a little better. There's a reason for that. It has to do with error. We'll worry about that later. Another mistake you can make is counting boxes. Please don't count boxes. You see our vertical axis, actually the boxes match the count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On the vertical axis, the count matches the boxes. Sometimes it does. The horizontal axis, not so fast. Look at this here. You can't do that nonsense. So 0, 1, 2, 3, 4, 5. No, that's a 2. That's not 5. That's a 2. And you could, of course, figure out how much each interval or each tick mark is worth by taking the actual magnitude there on the scale, on the axis, and then dividing by the number of boxes. So let's continue on this. Bad idea, counting boxes. Good idea, use the axes. You got to look at the numbers that are on there. Okay, last one is no units. Ignoring the units is a bad idea. Slope now has context. This is actually what we call a physical quantity. It means something. You can't say to somebody, hey, I did an experiment. Yeah, what's the result? Oh, it came out 22.2. What? Like I get 22.2 more years to live? You're going to pay me $22.2 for my bicycle? What is it? So no units is basically no sense. You need those units. All right. So let's come on down here. Let's look at a couple of questions, and then we'll do this real deal. By the way, over in the margin, you see vocabs giving you some tips. Here are the different ways we tend to write our equation for slope. Rise over run, which is not bad, by the way. You might think that's baby status. I like that one. It visually puts you in the right mood here. Rise over run, that's the same thing as delta y over delta x, which is the same thing as y2 minus y1 over x2 minus x1. Use whatever you want, they're all good. Notice over here, use the locations on the line, not necessarily, I'll probably write this in for you, not necessarily points from the data table. They might be on the data table, but the line is what wins. Use the scale, that's down here. Don't just count boxes, include units. And then this we'll get to later. You're not going to do a V slope for a curve. A curve has a changing slope. All right, so let's check this out. 822. Why is 822 no good when determining slope? So 822 is right here on the data table. So when you're doing this one, can you use it? You might think, all right, 822, cool. But here's the real deal. Go to 8. Here's 8. Go to 22. Here's 22. See where those two meet. 822 meets right here at this data point. Is that legit? Well, clearly not. No. It is not on the best fit line. If it's not on the best fit line, don't use it for slope. Next, can you use 2,5 when determining slope? Well, let's look here. 2,5 is in our data table. Data table automatically bad. Well, let's see. It really matters whether 2, 5 is actually on the line. Yes, we can use it. Why? Because 2, 5 is on the best fit line. So that's legit. Data table is not automatically bad. All right, as a shortcut, can you do 5 over 2? As a shortcut, is it okay to do 5 over 2? Well, back in the day, you might have done this and it may have worked. However, first off, is it okay? Well, generally speaking, no. It's literally the wrong method. But you might say, does it get me the right answer, though? And the issue here is, well, no. It doesn't even get the right answer. It's the wrong answer. And the reason it's the wrong answer, by the way, is right here. Let me clear some of this business up so you can have a look at it over here. Look here. You see this? This line does not go through the origin. Since it does not go through the origin, you see this spot right here. Since it does not go through the origin, then that first segment of line there up to the x-axis 2, up to this location where we're looking, the rise and the run are not 5 and 2. Is the rise 5? Yes, it is. But is the run 2? No! The run is actually, these are going by 0.4s. That's like a 0.2. So the run is actually like a 1.8. You get the wrong answer. This is not through the origin. And in case you ever use this, just dividing the coordinates of one data point, that's the game you were playing. You were like, oh, well, I don't even think about it, but if the line goes through the origin, then cool, I don't have to worry about it because you're minusing 0 on your y2 minus y1, and you're minusing 0 on your x2 minus x1. So if this went through the origin, you can get away with this. But if it doesn't, and it often doesn't, then no good. Remember, we're using real data in this course, and so real data is messy. It's not going to come out perfectly beautiful. All right, last practice one over here. Between the two circled locations, let me clean this up here so you can have a look at it. A lot of mess on this. Okay, here we go. Clear all this business out. Between the two circled locations, there they are. We got this one right here, and then we got this one right here. If you count this up, you will see in the y direction there's a rise of 20, and in the x direction there's a run of 19. Let's check it out. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yes, that gets us online with this. And then the run is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19. So it is 20 boxes up and 19 boxes right. So this right here, this is true. I'll show you what's true. It goes up 20 boxes, and it goes right 19 boxes. That's true. But the question is not 20 boxes, 19 boxes. If the y-axis represents meters or a distance, and the x-axis represents seconds or a time, is it 20 meters over 19 seconds? Is that legit? And the answer? No! No! Use the scaled axes. In this case, the rise actually was 20 meters. But the run was not 20 meters. The run here went from 2 up to about, what's that? That'll be 9.6. So 9.6 minus 2 is 7.6. That would be the right way to get this. You can't just count boxes. All right, so now it's time for us to actually do this one. Nice, blew this up a bit. I gave you the table, gave you the graph, determine the slope of the line. All right, so let's do this. 2-point format. 2-point format goes like this. First off, you need to know what we're working with. You're doing slope. Well, 2-point format, one of the things you want, we've been writing is 1, 2, 3. We're going to adjust that in a little bit, but that's fine. We can write it as 1, 2, 3 right now. It's not always bad to think about, too, like, oh, I'm finding slope. What's the equation for slope? Sorry, this formatting disoriented this board. It's already funky. All right, so this slope, we could use, why not use y2 minus y1 over x2 minus x1? That's fine. Fine. Well, if we're going to do that, in order to then solve for slope, over here, the physical quantity we're trying to find is slope. This one is going to come in meter per second, although it's not listed up here. Don't sweat it on this one. We're going to need y2 and y1 and x2 and x1. Now, there are different points you can use really technically anywhere along this line. But I'm going to warn you. If you choose like here and let's say here, you are going to make a large error. It's not going to come out correctly. If you choose those two locations, this is not going to give you a good result. In fact, your error will be such that you won't get credit. These need a wide stance. You've got to move them farther apart. In fact, what I'm going to strongly recommend you do is the following. I'm going to strongly recommend that you, let me try one of these darker reds. There we go. I'm going to strongly recommend that you just go to the edge of the line. Go all the way to where it hits the axis. Why don't we just use here and here? Now you may say, but that hits at an ugly spot. No, it doesn't. You have a brain and you can estimate. And take my word for this. I'll show you if you want to see in class or after class. If you choose these endpoints, even with your estimation, you will get a far better answer than these two narrow red points. The thing you don't realize is you're also estimating here and here. They're not dead on. This one right here looks like it hits right through that, but if you look closely, no, it doesn't. It misses. It's always an estimate when you're looking at this line. Heck, your pencil has thickness. Are you looking at the top of the line, the middle of the line, or the bottom of the line? You might say middle, but that doesn't mean it's right. Did you really draw it that carefully? So use the farthest possible points you can use. Locations. We'll call them locations so you don't think they have to come from the data table. If I look at this location has the coordinates of, the x coordinate looks to me, it looks like it's about in the middle of those two lines. So you could call that, we figured out before that these are 0.4, so maybe that's 0.2. I mean, I may even say it's a little more than that, but there's only so much you're allowed to as sig figs right there. So 0.2, this, by the way, was meters, and this was seconds. So 0.2 seconds, comma, that's an easy one in the y direction, 0 meters. So this is like your x1 and your y1. In fact, we can come over here and write these in. So my x1 is 0.2 seconds, and my y1 is 0 meters. Really 0.0, but let's keep going over here. Now I look at this one all the way over here. Does it hit that data point dead on? It's pretty close to the center. It's pretty close. You might be able to look here and cheat and say, oh yeah, I see what it is. It hits the middle of it. Even if it didn't, if I were to estimate this, my x coordinate I would put at 10 seconds. And my y coordinate I would put at 26 meters. You know, it looks awfully close to that. Could it be slightly off? Sure, but it's awfully close. So then I'll come over here. Here's my x2. Here's my y2. You may say, oh, but this is so slow. No, it isn't. If we do this step by step without all this talk and hubbub and you actually know what you're doing, this is fast. So x2 was 10 seconds and y2 was 26 meters. And believe me, when you get it wrong, you'll appreciate slow more than fast. So let's go over here. We got everything we need. Run it. Slope is y2 is, where is this? 26 meters minus y1, we got 0 meters. Over x2, we got 10 seconds minus 0.2 seconds. Okay. And so then you get to your answer. Slope equals, you can do an intermediate step. By the way, I'm going to put something in black. I don't actually grade this next step right here. Slope equals 26 meters over 9.8 seconds. But, you know, if you want to write it, write it. It's not a bad thing. And so then you do 26 divided 9.8. Let me check out the calculator. 26 divided 9.8. I got about 2.65 meter per second. And so if we're going to do this to two sig figs, depending on how closely you estimated these, you're going to get something like 2.6 to 2.7 meter per second. You may have estimated a little differently than I did, but there it is. That is the clean and correct way to do slope. Get it right.